Texas A&M tests tiny robots to recover lithium from seawater. A Texas A&M University research team is exploring whether microscopic, fish-like robots could recover lithium from seawater, potentially creating another supply option for battery and energy storage manufacturers. The project has received a $1 million award from the U.S. Department of Energy. It is one of 19 federally funded initiatives focused on expanding domestic access to critical minerals and reducing supply chain exposure. Rather than relying on fixed membranes or large stationary treatment systems, the proposed technology would use mobile micro and nanoparticles designed to move through seawater and interact directly with lithium ions. An external energy source, such as light, would activate the particles. After capturing lithium, the materials could be collected using magnetic fields and, in principle, prepared for another extraction cycle. Seawater has scale, but lithium is hard to isolate. Most commercial lithium is produced from hard rock deposits or concentrated underground brines. Those resources are located in a limited number of regions, creating sourcing and geopolitical concerns for battery manufacturers, automakers, and energy storage companies. Seawater offers a much larger theoretical resource base. The challenge is concentration. Lithium is present in the ocean at very low levels and is surrounded by far greater quantities of sodium, magnesium, and other dissolved minerals. Any viable extraction system must be selective enough to capture lithium without using excessive energy, materials, or processing capacity. Recovering small quantities from enormous volumes of water could quickly become uneconomic if the particles also collect competing ions or require frequent replacement. The Texas A&M team will examine whether mobility improves contact between the extraction material and lithium ions. By moving through the water, the particles may reduce the need for extensive pumping equipment or permanent offshore infrastructure. That potential advantage still needs to be demonstrated under realistic marine conditions. The research is being led by Shiren Wang of Texas A&M's Department of Industrial and Systems Engineering and Jingjing Jenny Chu of the Department of Mechanical Engineering. The work brings together nanorobotics, materials engineering, and marine system testing. Commercial viability will depend on recovery and reuse. The project remains at an early research stage. The team plans to test lithium selectivity, material durability, and particle performance over repeated extraction cycles. Researchers will also need to determine how reliably the microscopic materials can be recovered from the water. Particle loss could raise operating costs and create environmental concerns, particularly if the system were deployed across large marine areas. Other commercial questions include the energy required to activate and retrieve the robots, the cost of manufacturing them, their ability to withstand saltwater exposure, and the infrastructure needed to process the captured lithium. Even a technically successful system would have to compete with established mining and brine extraction operations. That means performance will ultimately be measured not only by how much lithium the robots collect, but also by cost per unit, energy use, recovery rates, and environmental impact. The researchers aim to develop a continuous process in which the materials can be retrieved and reused multiple times. Their work will include lithium recovery characterization, larger-scale performance testing, and an assessment of potential environmental effects. For battery and clean energy businesses, the project is not yet a near-term replacement for conventional lithium production. It does, however, show how federal critical mineral funding is moving beyond traditional mining projects and into technologies that could diversify future supply. If the team can address containment, durability, and economics, mobile extraction systems could eventually complement existing lithium sources. Until then, the main test is straightforward: whether tiny robots can recover enough lithium to justify operating at ocean scale.